So in the last section, we learned about logarithms and what they are. And in this section, we're going to learn some properties of logarithms that are going to be important to know about if we're going to see how they work. So first of all, logarithmic and exponential functions are inverses of one another. And that means that a to the log base a of x is just x, or log base a of a to the x is just x. So if you start with a logarithmic function, then apply an exponential function, or if you start with an exponential function and then apply the logarithmic function with the same base, you're back where you started. In particular, that means that 10 to the common log of x is just x, and log of 10 to the x is just x. So start with any number, take the common log, take 10 to that power, you're back where you started. Start with any number, take the natural log, then raise e to that power, and you're back where you started. Or do it the other way around. Take e to the x, then take the ln of that, you're back with the x that you started with. So, for example, the log base 7 of 7 to the 20th power is 20. That's an example of this property right here, where the part of a is being played by 7 and x is 20. The ln, that is the natural logarithm of e to the negative 59, is negative 59. That's this one right here. 9 to the log base 9 of 77 is 77. That's this one right here. E to the ln of 10.2 is 10.2. That's this one right here that I forgot to put the equal sign in. Now, we have three important properties that relate multiplication to addition, division to subtraction, and exponentiation to multiplication. So let's take these one at a time and see how they work. If you ask your calculator for the log of 4, and remember that means the common log or base 10 log, it'll tell you that that is 0.602059991. If you ask it for the log of 100, it'll give you just 2. And if you ask it for the log of 400, it'll give you 2.602059991. Notice something here. 4 times 100 is equal to 400. But when you look at what we got for the logs, 0.602059991 plus 2 equals 2.602059991. So the log of 4 times 100 is equal to the log of 4 plus the log of 100. In a way, the log turned multiplication into addition. So that's the first of those three properties I was showing you. Log to any base, so this applies to common logs, it applies to natural logs, or any other base logs, as long as it's the same base all the way across. The log of u times v is equal to the log of u plus the log of v. Here the u and the v stand for any numbers or any variables or expressions that stand for numbers. For example, the log of 7 plus the log of 3 would equal the log of 21. And the log of 2 plus the log of 5 would equal the log of 10. And turns out that the log of 10 is just 1. So this is something you can try on your calculator. Ask it for the log of 2, it'll give you some weird number, point something something. Ask it for the log of 5, it'll give you point something something. But when you add those two numbers together, they add up to exactly 1. And if you remember that list of numbers we were playing around with the last couple days, we saw how, like, if you take the 5th number on the list times the 10th number on the list, you get the 15th number on the list. That's because of the way exponents work. But you can also look at it as being because of the way logarithms work. The base 3 logarithm of 243 is 5. The base 3 logarithm of 59,049 is 10. When you multiply those numbers together, you get 14,348,907, and the base 3 logarithm of that is 5 plus 10, or 15. And in fact, this property was very useful back in the days before calculators and computers. So for centuries, before people could just pull out a calculator or a computer and use it to multiply two big numbers together. If you wanted to multiply two big numbers together without actually sitting down and multiplying it all out with pencil and paper, one thing you could do is you could get a table of logarithms, something that looks a little like this. You could look up the two numbers that you wanted to multiply and find their logarithms, and then you'd add those logarithms together and then go back to the table and see which number that corresponded to. So by using a table of logarithms, you could turn a multiplication problem into an addition problem, which would be easier to do if all you have is just pencil and paper. And you could turn a division problem into a subtraction problem using one of the other properties that we're going to look at in just a second. And you could turn a problem of raising a number to a power into a problem of multiplying a number by another, hopefully, little simple number. So that particular use of logarithms isn't nearly so important nowadays, now that everybody has easy access to calculators and computers that can do your calculations for you. But it used to be a really big deal and something that if you were going to be doing calculations like that, you would want to learn about and be able to use. So in the old days, many math books would come with a table of logarithms in the back. Find a algebra book from like the 80s or earlier and look in the back, you'll probably find a table of logarithms and a section that explains how to use it to do calculations. Now here's the second property, the one that relates division to subtraction. Let's start with an example here. You can ask your calculator for the log of 37,000. You probably wouldn't put in the comma when you're putting it into your calculator, but I put it in to make it a little easier to see what the number was. The log of 37,000, your calculator should tell you that's 4.5628201,724. Then ask it for the log of just 37, and it'll give you 1.568201724. And then if you subtract those numbers, the 4 point something minus the 1 point something, you get 3. And that's the log of 1,000. But 1,000 is 37,000 divided by 37. So that shows that the log of 37,000 divided by 37 is equal to the log of 37,000 minus the log of 37. It turns division into subtraction. Try another example. What's the log of 12 minus the log of 2? It is the log of 6. It's log of 12 divided by 2. And on those lists of numbers that we were playing around with the other day, we saw how you can take two numbers on the list and divide them, and that's like subtracting their logarithms, like the number that is the 17th number on the list, so the base 2 logarithm of that number is 17. If we start with that number and divide by the number whose base 2 logarithm is 14, we end up with the number whose base 2 logarithm is 3. And the third of those properties, the log to any base of a number to a power is equal to the power times the log of just that number. So here's an example of this property in action. If you ask your calculator for the log of 4, It'll tell you that's 0.6020599991. The log of 16 is 1.204119983. But 16 is 4 squared. And the log of 4 squared is 2 times the log of 4. The log of 4 is about 0.6. The log of 16 is about twice that, 1.2. And what about the log of 64? That is the log of 4 to the third power. Well, that's about, well, it is 3 times the log of 4. It's 1.8061799974. So the log of 4 to the third power is 3 times the log of 4. So in general, the log of something to a power is equal to the power times the log of the something. And vice versa. All of these go both ways, and sometimes they're useful in one direction and sometimes they're useful in the other direction. So 2 times the log of 7 is equal to the log of 7 to the 2 power. That is the log of 49. So I'm going to end this video right here, and then I'm going to come back in part 2, and we will practice using these properties in both directions to rewrite or rearrange some logarithmic expressions. See you then.